Have you ever really stopped to think about how something like, say, the sound of a guitar string actually gets into your phone? I mean, it's pretty wild, right? Well, it all comes down to a translation between the two fundamental languages our technology uses, analog and digital. In this explainer, we're going to decode these languages and see how they literally shape every single piece of tech we use every day.
So let's stick with that idea. How does the sound of your voice, which is really just a vibration traveling through the air, somehow end up as a file on your phone? It kind of feels like magic, but it's not. It's all about that translation process, and that's exactly what we're going to unpack right now.
You see, the answer is that your voice, and pretty much everything else in the physical world, can be represented as a signal. Just think of it like a continuous flowing wave of information. So the big challenge for any piece of technology, whether it's an old-school record player or a brand new smartphone, is how do you capture that wave accurately? Okay, so how do we actually capture that wave? Well, the first and, most intuitive way is what we call the analog approach. The best way to think about it is like you're making a perfect but physical copy, an exact impression of the real thing.
So analog signals are continuous. They just flow without any breaks, exactly like the sound wave of your voice. The whole goal with analog is to create a perfect mirror image of that reality, capturing every single little nuance. It's kind of like pressing a key into clay. What you get is an exact physical imprint of the original.
And this is where analog really shines. Because it's a direct copy, it can achieve this incredible fidelity, especially when it comes to audio. This is exactly why so many audiophiles still swear by vinyl records. The sound wave is literally carved into the groove of the record, creating this true, uninterrupted representation of the original music.
But, and this is a big but, here's the catch. Analog's greatest strength, the fact that it captures every single tiny fluctuation, also happens to be its biggest weakness. Let me show you what I mean.
Because an analog signal is this perfect physical copy, it's also incredibly fragile. I mean, think about it. Any little bit of interference, any speck of dust, any wear and tear over time introduces noise. It's like a smudge on a perfect painting. A scratch on a vinyl record isn't just missing data. That scratch becomes part of the music itself. It's a perfect copy, sure, but it's a copy that's really, really easy to damage.
So, to get around this whole fragility problem, engineers came up with a totally different way of thinking, the digital method. Instead of making a perfect copy, what if we made a precise blueprint instead? Let's see how that actually works.
Right? So instead of making that fragile physical copy, digital processing creates a precise set of instructions, a blueprint. It doesn't even try to mirror that continuous wave. Instead, it measures the wave at very specific points and then converts those measurements into a language of numbers, and that language is binary code, just zeros and ones.
So how in the world do you turn a smooth, continuous wave into a bunch of code? Well, it's basically a three-step process. First, you start with that original analog wave. Then, the system takes thousands of little snapshots or samples of it every second. And here's the amazing part. Thanks to something called the sampling theorem, we know that as long as you take samples at least twice as fast as the highest frequency in the signal, you can perfectly rebuild the original wave later on. It's incredible. Finally, each one of those measurements gets converted into a string of ones and zeros. And what you end up with is something that looks kind of like a staircase that follows the shape of the original wave. Now, it's obviously not a perfect, smooth copy, but because of that sampling principle we just talked about, it's a super precise and, more importantly, durable set of instructions for rebuilding that wave with almost no loss of information.
And this is the real game changer. A stream of ones and zeros is incredibly hard to mess up. A little bit of static on the line isn't going to magically flip a 1 to a 0. This is what makes digital information so ridiculously robust. You can copy it 1,000,000 times, and it will be perfect every single time. You can edit it with pinpoint precision, and you can send it all the way across the world flawlessly.
Okay, so we've got two totally different philosophies here, right? On one side, you have the perfect but fragile copy, and on the other, you've got the precise but sort of approximate blueprint. So let's put them head to head and see how they stack up.
This table really lays it all out pretty clearly. Analog is continuous, digital is discrete. Analog is super susceptible to noise, digital is highly resistant. And just look at the flexibility. I mean, it is so easy to edit a digital photo because all you're doing is changing numbers in a file. Trying to do that same kind of edit on old-school photographic film, that is a whole different ballgame. It's a physical, chemical process that really just highlights how powerful and reliable digital data is.
So after all that, which one is better? Well, you know what? That's actually the wrong question to be asking. The real question is which one is the right tool for the job.
Yeah, the biggest takeaway here is that analog and digital, they're not enemies fighting for supremacy. They're just different tools in the toolbox, each with its own strengths. It all just comes down to what you're trying to do.
Analog is still the king when you need to capture the most natural, high-fidelity signal you possibly can. Think about the microphones in a professional recording studio. They need to capture all the warmth and subtle nuances of a human voice. Or think about those classic tube amplifiers that give electric guitars that rich, iconic tone. An even better example is an ECG machine. It has to capture the continuous, delicate electrical fluctuations of a person's heartbeat without any approximation. That's a job for analog.
But for pretty much everything else that involves storing, copying, editing, or sending information, digital is the undisputed champion. Your smartphone, the internet, cloud storage, all of it is built on this incredibly robust, flexible foundation of ones and zeros. And look at something like medical imaging, an MRI. It takes thousands upon thousands of discrete data points to build a complex, editable 3D model of the human body. That's a feat that would be absolutely impossible with analog technology.
So I want to leave you with this final thought. We live in a smooth, continuous, analog world, but more and more we experience that world through discrete, digital technology. Now, this translation from a wave to a blueprint is unbelievably powerful, but it's never absolutely perfect. So as we continue to digitize more and more of our reality, it's worth asking, what are we leaving behind? What essential details, what subtle nuances might be getting lost in translation?